Hello and welcome back. We'll finish up section 6.5 in this video, and we'll look at an example of how to construct a normal quantile plot. This is one way of determining whether or not a data set is normally distributed. So there's essentially 4 steps, and the first step is very easy. We just want to arrange the data from lowest to highest. Okay, so we'll just sort the data. Next, we'll need to come up with some numbers, and these numbers have a very particular meaning. I'll go through in a quick example afterwards where these come from. But because each of the n data points represent 1/nth of the data, we need to find certain values. And it's 1 over 2n, 3 over 2n, 5 over 2n, just going on until we have n values in this pattern. So for instance, if n was 20, we would go 1 over 2 times 10 is 20, so 1 over 20, 3 over 20, 5 over 20, all the way up to 19 over 20. Okay, we'll use these values in the next part, where those values are values between 0 and 1, and they're going to represent areas in the normal distribution. So if we imagine that we have a normal distribution, we're going to be using these areas to say, oh, we want to find the z-score that corresponds to this area here. So this would be 1 divided by 2n, for instance, or 3 divided by 2n, and then 5 divided by 2n, and 7 divided by 2n, all the odd numbers on top. So we'll find a z-score for each one of those, and then this is what we plot. We have the individual data value and the z-score. So I want to talk about this pattern and where this comes from before I go through a more explicit example. So let's say that we have 4 data values. Those 4 data values will be essentially describing the entire data set, and if we sort the data, we can talk about, okay, so we'll have one data point representing the middle of this interval. We'll have one data point representing the middle of this interval, middle of this interval, and the middle of this interval. And we want to know what is the cumulative probability. So what is the probability of scoring less than this point? Well, if we split everything up, we've split up our area into four pieces. So this is 0/4, 1/4, 2/4, 3/4, and 4/4. But if we're only looking at the area to the left of this is half of this region. So this is in fact going to be 1/8. If I look to the left of this guy, this is going to be 3/8. To the left of this one will be 5/8, and to the left of this guy is going to be 7/8. And this is not something that you have to draw a picture of every time. We can find these pretty easily. With 4 data values, we want 1 over 2 times 4, which is going to be 1/8. We want 3 over 2 times 4, which is 3/8. 5 over 2 times 4, which is 5/8. And 7 over 2 times 4, which is 7/8. So it's just those 4 numbers. You don't have to draw this picture. We can just be counting up. So it's 1 over 2 times n, 3 over 2 times n, 5 over 2 times n, 7 over 2 times n, and we'll just keep going until we have 4 values. So let's do this in an actual problem. Let's draw the normal quantile plot for how long Old Faithful erupted for in seconds. So we have five values here, and I'm going to do everything in StatCrunch. So if I come over here to StatCrunch, I have inputted these data values already. Maybe I can call this, so this is Old Faithful seconds. So these are all the seconds that Old Faithful erupted in 5 times. The first step is always to sort the data, and I want to sort it so that it goes from lowest to highest. Okay. So the next part was to come up with these numbers. So again, 1 over 2n, 3 over 2n, and so on and so forth. 1 over 2n. Well, n here, there's 5 values. So 1 over 2 times 5 is 1/10, or 0.1. The next data value will be 3 over 2 times 10, so 3/10. Then 5 over 2 times 10, which is 5/10. 7 over 2 times 5, and 9 over 2 times 5. So you can see that these are all equally spaced. These are fairly straightforward to come up with. And now I want to know the area that each of these numbers corresponds to in the normal distribution. So if I come to stat calculators and come down to the normal distribution, we have our normal graph again. And let's see here, I just put this place so we can see it. So I want to know, so we're looking at the area to the left, and for our first value, which is going to be 0.1, this corresponds to a z-score of negative 1.28, essentially. So this z-score, the area to the left of this, corresponds to 0.1. So the probability of getting a number less than this z-score is going to be 0.1, which is the number that we want. So I'll copy and paste this in here. Next, we want the area for 0.3. Notice that it's a bigger area now because 0.3 is bigger than 0.1. So we will copy and paste this in here. Then we'll have 0.5. And what we'll recognize with 0.5 is that's exactly half of the area. And since the normal distribution is symmetric, half the area is going to be right down the middle. And the middle for our standard normal distribution is 0. So we could do that calculation without having to use this calculator. However, the rest of them would be nearly impossible. So for 0.7, we get this value. And then for 0.9, we'll get this value. So let me exit out of this. One thing that you'll notice is that this top value and the bottom value are exactly the same, but negatives of one another. Again, this is because the normal distribution is exactly symmetric. If we're looking at a normal distribution and the area to the left is equal to 0.1, down here, when the area to the left is 0.9, if you flip it over, the area to the right is 0.1. So these numbers are very similar in relation to the normal distribution, so these numbers will be negatives of one another. The last step is to plot the graph. So we want to come over to graph. We want to make a scatter plot. And the first variable will be the seconds that Old Faithful erupted, and the y value is this column, which we hadn't named yet, so it's just variable 3. And there are no other options that we need to explicitly mess around with. So we will compute this, and we get ourselves this graph. And when we look at this graph, this doesn't look like a straight line. These kind of do, but this one is off to the side. So any sort of straight line wouldn't be able to pass through all of these points, not even close. So what can we conclude? Since this is not a straight line, these data values are not normally distributed. Okay, so just to repeat that, these points do not form a straight line. Therefore, the values probably do not come from a normal distribution. So this is how you plot the normal quantile plot. Again, you arrange your data values in ascending order. We calculate the areas to the left, which are just going to be 1 over 2n, 3 over 2n, 5 over 2n, just an odd number over 2n. We find all of these areas. There's the corresponding z-scores in the normal distribution, and plot it. So if I come back here for a second, so find the normal quantile plot, we did that, and we determined that these values don't come from a normal distribution. In fact, just relying on some old knowledge, this should be a bimodal distribution, but that's neither here nor there. The very last thing that we'll look at is transforming normal distributions. So it turns out that there's a few ways to take a normal distribution and change it just a little bit so that it still remains a normal distribution. So for instance, if you just add some number to everything in a normal distribution, let's say you just add 100 to all of your data values, all you're doing is you're taking the normal distribution, and we are shifting it over so that if we look at our new normal distribution, it should be roughly the same, except that the mean will have shifted over by some constant if we just add c to it. The same thing happens if we multiply by a constant. We still get a normal distribution. If I draw this over here, if I say double all of the values in a distribution, say just multiply by 2, the normal distribution won't look quite the same, but it's still going to be a normal distribution. It's just going to be a lot wider. This is going to be a wider normal distribution. But adding a constant gives another normal distribution. Multiplying by something that's not 0 gives a normal distribution. These are common ways of changing normal distributions into ones that are easier to work with. However, we should be careful taking logs, taking exponents, like squaring distributions or taking square roots. Don't usually preserve normality. So if you take a normal distribution and you do something to it that's a little bit funky, you can get something that's not a normal distribution. These are still useful. They appear in nature. For instance, log normal distributions that have been affected by a logarithm, show up quite often when looking at sizes of things or lengths. So for instance, when you look at human lifespans, they tend to be log normal distributions rather than a normal distribution. So adding and multiplying normal distributions preserves normality, but many more things don't.